Machine learning is being widely used in cybersecurity nowadays. However, it's very common to notice some pitfalls and challenges that most of the time are not covered in the literature. I am Fabrício Ceschin, a PhD student at Federal University of Paraná, Brazil, and I'm going to help you spot the differences and show you the quirks of machine learning in security. Of course, you can interpret the title however you want. It's up to you. So today, a massive amount of data is produced, and as a consequence, new emerging threats are constantly being developed by attackers, increasing the losses in the past years. Thus, machine learning is considered the state of the art and the ideal ally to build automated solutions to detect attack vectors. However, cybersecurity has many peculiarities that are not inherited from other fields. OK, but why is machine learning for security different? I will show you a classical example of why. Imagine a simple image classification problem. We want to create a model to classify cats and dogs. This model will not change as time goes by. Cats will always be cats, and so the dogs. They always look the same. So we do not need to update the classification model every time a new dog or cat appears. We just need a population that generalizes both classes, right? In cybersecurity, we have a very good example with phishing. According to Google, 68% of phishing emails blocked by Gmail are different from day to day, which means that their distribution is non-stationary. Here we can see images from the very same Google Drive page updated by the attackers over time. So they update the phishing page over time to evade classification, to evade the detection over time. As a consequence of that, the literature says that blindly applying machine learning evaluation best practices may backfire in security contexts. OK, but how do I know about it? When I built my first malware detector with machine learning back in my master's, the questions were the same as any machine learning task. Which data set to use, what features, which models, what metrics. After some research and experiment, I ended up publishing a paper where I achieved 98% of accuracy. Seems good, right? Years later, there was a machine learning evasion competition, which objective was to submit a model that detects variants of malware developed by the attackers. I thought, my model achieved 98% of accuracy. Of course, it's going to detect everything in this challenge. We are going to win, right? But it was not what happened. My model did not achieve the desired performance. It did not detect the majority of samples developed by attackers, and my team finished in the second position. In the end, it was very similar to a fast food ad. We had an expectation and finished with another reality, right? And now I'm here to tell you what is different in cybersecurity and why we need to take care when using machine learning algorithms. So let's start by talking about the dataset definition, which is the first step to building a solution. So defining a dataset is a challenge that is normal in any machine learning domain, but this can have severe implications for security. So first, it's very difficult in security because organizations generally do not share data in order to not reveal their vulnerabilities. On one hand, small data sets may not be representative of a real scenario, which may invalidate the result of possible experiments using them and may not generalize it enough. The solution may not work as intended, presenting a poor classification performance in practice. And on the other hand, very large data sets can have long training times, produce very complex models, which can make the model not feasible in the real world. This is very common in deep learning models, which often need a large amount of data to show good results. In the words of George Box, mentioned in the majority of machine learning books, essentially all models are wrong, but some are useful. In our context, models built using a dataset can be useful for a given task. It might not be perfect, but we need to know how wrong it needs to be by selecting a false positive rate threshold, for instance, or any other metric. Finally, it probably won't be good at other tasks. We need to collect new data or select new model parameters if you want to use it for other tasks. Alfred Korzybski, a very known in system theory, also has an interesting code that says that The map is not a territory. It is just a symbol, index, or representation, but it is not actually the place itself. That is, a map is subject to errors, just like a dataset. It can represent a real scenario, but it can only be a representation of it and may contain errors. In addition, we are often faced with the anchor bias, which makes us think that a larger dataset is better, making it a new baseline for future comparisons. As a good example is thinking that a dataset with 1 million samples is better than a smaller dataset. However, such a fallacy is not true. It's not about size. It's about the representativeness of the real world for the task at hand, just like a map. So here we have the ENIGMA Hotel Map as an example. Let's say that our objective is to get to the conference hotel room from an airport nearby. As we can note, this map is great to know which airports are near. So we can use this information to locate ourselves and get to the hotel, right? However, if we use the Santa Clara restaurant maps for the very same objective, it won't work and won't represent our problem. This is very similar to a dataset, right? To show that dataset size is not relevant as we may think, I performed 2 experiments that consider different proportions of the dataset in both training and test sets. Here I used a subset of Undersampling dataset containing almost 300,000 samples. The samples are randomly selected for each proportion. And in the experiment 1, I compared different classifiers using a temporal classification, splitting the dataset into 2 sets ordered by time. So the training set has the oldest samples, as a real solution should do. The results show a pattern for all classifiers, which have unoptimal results obtained using only about 10 and 20% of the dataset. In experiment 2, I tested different evaluation approaches like cross-validation, temporal classification, and data string with and without drift detection in the same classifier, which is the random forest. All of them also show a pattern and stabilize the results using around 30 to 40% of the dataset. Finally, it's possible to say that a dataset is not about size. It's just about the representativeness of the real world for the task at hand, just like a dataset, just like a map, once again, right? So another problem that we can face in cybersecurity is class imbalance. By definition, class imbalance is when the class distribution of a dataset differs relatively by a substantial margin. This problem is very common in real-world research, since it may be difficult to find malicious samples. A good example is the Undersampling malware dataset, which has only 18% of malware samples. The literature has several methods to solve this problem, but here we are going to focus on the pre-processing strategies based on resampling, which consists basically in removing samples or creating new ones. The undersampling method consists in removing samples from the majority class. So consider a dataset with 2 classes, green and red, with the second class containing 2 subclasses or 2 concepts, for instance, 2 malware families that evolve over time. The first image shows the original distribution of the dataset without any resampling technique. In the second figure, a conventional resampling technique is used without any temporal information. As we can notice, the result is different from the reality. The distribution of malware families or subclasses has changed and no longer represents the original dataset, which can lead to a biased model. In an ideal scenario, the undersampling technique should consider the temporal information of the dataset, keeping the very same proportion of subclasses from the majority class as time goes by, resulting in a more realistic scenario as we can see in figure 3. The oversampling method consists in generating new samples from the minority class. Now let's consider a dataset similar to the one presented previously, but now with the majority class being the green one and the minority being red. Again, we have 2 subclasses or concepts, red and orange, as shown in the original distribution in the first figure. In figure 2, we can observe a conventional oversampling technique that does not take temporal information into account, creating new samples with features of both subclasses, even in periods when the orange concept does not exist, both orange or red, right? As noticed, the resulting dataset no longer represents the original one, which can lead again to a biased model. So we have a problem. In an ideal scenario, where we consider the temporal information, the oversampling technique should consider subclasses when generating new instance, maintaining the original dataset proportion by using the temporal information, as we can see again in figure 3. I could not present this work without talking about adversarial machine learning. So the generation of adversarial samples is a very common problem in machine learning for security, because attackers are trying to generate adversaries that look similar to benign samples. In the smart detection example, we can see that it is possible to create a fully functional malware that bypasses the detection of machine learning models. For this, giving an original malware that is detected with 91% of confidence, an embedding function that embeds the malware inside another binary, and a set of benign files, it is possible to generate an adversarial malware that has an even higher confidence than a good one. In this case, 92% of confidence. We can note the effect of the adversaries created using this strategy in real antiviruses. I submitted 50 malware samples to VirusTotal, including the evasive variations. And as we can note, the evasive samples have lower detection rate than the original ones, indicating that AVs are also working with machine learning models under the hood and are also affected by this simple strategy. Possible mitigation to deal with new attack vectors is to update the classification model after we have their labels. To simulate the situation, I trained 2 classifiers. The first one with no adversaries in the training set, using only the Ember dataset. And the second including adversaries generated in 2019. We tested both models with 2 test sets, one with the 2020 original malware samples, and the other with adversarial variations of this malware from 2020, both sets with Windows apps as benign applications. As we can see, the model trained with no adversaries is able to detect our original malware samples and the majority of good ones, with a very low false positive rate. In contrast, it did not detect the adversarial variations of the original 2020 malware samples, so it's not detecting adversarial malware. In addition, the model trained with the adversaries detected all malware samples, even the adversarial ones, with the cost of labeling the majority of good samples as malware, which makes its use unfeasible in practice because it's basically saying that all samples presented are malware. So finally, we can say that in practice, just updating the model with adversaries is not enough. We need new strategies to deal with this problem. The last step in creating a solution is the evaluation, where we have the problem of the delay labels. One of the challenges in evaluating security solutions that use machine learning is the delay in making labels available. This directly affects how the evaluation is done, since labels do not exist right after the data is collected. This problem is not considered by many works. They consider that labels are available right after data collection. Some works consider that the unlabeled data have the same label that the machine learning model predicted, which can be a problem since the model may be vulnerable to poisoning attacks, decreasing its detection rate over time. In malware detection, for instance, just a simple snapshot of the VirusTotal scan is used without considering the label's delay. According to the literature, malware labels can vary from 10 days to more than 2 years. Furthermore, AV solutions take about 19 days to detect most threats. To verify the impact of labels delay, I simulated the situation using a subset of the Undersampling dataset again, using the adaptive handle forest with and without drift detectors as a data stream. For this, I'll make the labels available for the classifier to be updated only after n days it was first seen. Only then the decision model is updated with the new data. By observing the results, when there is no delay, the algorithm with the drift detector improves detection with almost 100% recall and precision. So seems like the ideal scenario. After a day of delay, the model that does not consider drift turns out to be better overall, indicating that the drift detectors are highly affected by delays. In practice, machine learning models do not perform as they are commonly evaluated without considering these delays in the labels. So now concluding the talk, the future of machine learning for security is promising. machine learning has become so popular that it's hard to imagine a future without it. However, there is still a lot of room for improvement, such as the following recommendations. We should stop looking only at metrics and start looking at the facts. Many of the challenges presented in this work remain as open research problems, which would benefit both academy and industry if properly solved. In addition, their mitigation would foster the use of machine learning for cybersecurity problems and improve the cybersecurity field in the same way machine learning improved and advanced other research fields. Community players have to take into consideration the peculiarities associated with cybersecurity data and its sources. Also, commit yourself to the real world. I advocate that future research works always keep the motto, machine learning that matters in mind when developing new solutions. We need to stop trying to improve 0.01% of accuracy while we are still evaluating our models or our solutions in the wrong way and have many open research problems such as the ones mentioned here. Thus, if your work is losing connection to the real world, we have a problem. Finally, check your work. My recommendation is to carefully observe all the items and to consider each of them during the design and implementation of machine learning models for cybersecurity. To encourage that, I present a checklist to serve as a reminder and prevent researchers and practitioners from committing these common mistakes, or at least being aware of their existence. You can access this checklist through the URL or this QR code. I would like to finish my presentation with a quote from Ayrton Senna, which says that the past is just data. I only see the future. So let's look to the future and start working for a better machine learning and cybersecurity community. Thank you for your attention and for your time.